The second part of my lecture, of the lecture of total and effective stress, is the stresses due to external loads. In the first part, we were discussing the internal stresses, which is the stresses due to own weight. Part of it will be carried by water, part of it will be carried by the soil, and so on, how this will happen. This was all what we were discussing. It's just the weight of the own weight of the soil. Now suppose that I have now additional loads. I have a building, I have a load that is a concentrated load, a line load, a loaded area. It is an additional load to the soil. Whether this additional load will be carried by the soil or carried by the water, this is something else. But now I'm not concentrating who will carry it, but this additional load, it is with a certain value on top of the soil. Will it be the same as I go deeper, or will it be reduced? It should differ. The additional load is different because it is only on the top of the soil. But the own weight is all the way down. If I'm speaking about 4 meters of clay, it is 4 meters of clay. But if one person standing above 4 meters of clay, then his load is limited to the place where he is standing. What will be the effect of his load on all of the 4 meters below? I should know. Of course, if your weight is 70 kilos and you are on top of the clay, so the load is 70 on top of the clay, or the stress, we can calculate the load divided by the area. So I can reach the stress. But what about this load maybe at 2 meters below the ground? Will it be the same? Will it give the same stress? It will differ. How? This is what we should know. So scientists or people studying geotechnical engineering try to propose methods for me to understand the effect of this load on the ground. Of course, we are doing all of this. Why? Because it's our target. Our target is to design foundations. So if I cannot design foundations, then I have a problem. I need to understand, I know the load P. This load P, I can divide it by the area here, B by L, and I can get stress. This stress is at this location. If I go 10 meters below, what is the effect of this stress? Will it be there? Will it be diminished? Of course, it should diminish. Why? Because if load is transferred without a reduction, it means that if I have load and it is transferred without reduction, it means that all the loads of all of the buildings and the people will meet at the core of the earth, because no, it should end up at a certain level, and it has no effect beyond this. Some definitions. Contact stress. Contact stress is the load divided by the area. We just said this. Foundation depth, of course, it is the depth, the depth below ground for the foundation. Rigidity of the footing. This is very important in engineering sense. Is not in what we are going to study. Rigidity is very important. If I bring you this mouse and I push this mouse down, computer mouse, this computer mouse will push the table below it. Why? Because this mouse is rigid. When I put a load on top of it, the load is distributed all around this area and it pushes the ground. But if I take a piece of cloth or a piece of paper and I just put my finger on top of it, would I expect that the paper will push the ground? No, my finger will push the ground because this piece of paper is very flexible, it's not rigid. So one very important factor in design of any foundation that it should be rigid. If I have flexible foundation, then I should have a method for designing a flexible foundation. Because what is a flexible foundation? It means that the stress below the column will be maximum, the stress at the edges will be minimum because it is flexible. It can move. So the area beneath the column will take all of the stress, and the other areas may be zero at the edges in some cases. So rigidity of the footing, it is the contact stress distribution under the footing. The contact stress distribution under the footing depends on the rigidity as shown in the figure. If I have various types of footings, one of them is flexible, one of them is rigid, and so on, the stress of the soil will differ according to this. This is important that you know as an engineer, that if you have a flexible foundation, you expect the maximum stress to be where? At the middle or at the sides, and the opposite in case of, if this is flexible, then the opposite will be for case of rigid. Here is flexible footing, so this is the shape of the stress. So this is the stress here, and here is a rigid footing, and this is the stress. Of course, it is not only the rigidity of the footing, it's the interactive rigidity between the footing and the soil, because it differs. If I have flexible footing on rigid soil, it is different than flexible footing on flexible soil, and so on, or weak soil. So it's not only the rigidity of the footing, it's how much the soil is strong, because on rock, the behavior of a footing will differ than the behavior of a footing on soil. It differs. Point load. In case I have a point load, I just have a concentrated load on top of the soil. What will be the effect? What will be the value of this load at a level below it, or maybe not just a level, a distance away from it? Suppose that I have a point load here, point P, and I tell you I want to know the effect of the stress of this P at a point that is Z below this point, and R to the side. So in this case, I need to calculate sigma Z due to P, which is the stress due to the load P. Scientists gave us some charts. We can use these charts and an equation. They said that sigma Z, the one that we need to calculate, is equal to P. This is the load. But P divided by Z square, so it is affected by the square of the depth, which means that the more you go below, there will be a termination for the stress, because the stress is divided by the square of the depth. So this is one thing. What about the effect of the distance? The effect of the distance is given by something called IB, which is an influence factor. This influence factor I can deduce from this table or from an equation. This is the equation of the table. I just substitute with the factors. Here it depends on the R by Z. I get the value of R by Z, move upward, then horizontally to get the I, substitute in this equation, then I can get the stress due to a point load at any location in the ground. Suppose that you have a line load. Instead of having a point load, you have a line load. You know what is the difference? Of course, a point load similar to a column. A column will have a point load, but a wall will have a line load. So suppose this P is just, it is not P, it is P dash, because it is P by meter, every meter. It is there every meter. And I want to know exactly the same. So what I do, of course, at a point below a point Z and at a distance, horizontal distance X, then I use the same way. I use this equation, I use this influence factor diagram, and get the effect of sigma Z at any location below the ground. Example. You have a column load at a building are represented by point loads as shown in the figure. So I have here this one column load, these are the column loads, and there is a wall. So I have point loads and I have a wall, and I tell you, please calculate the stress at point A. But not at point A, at point A, at a depth of 4 meters below the ground. So I will study each one alone, get the effect. If I am now here 4 meters below point A, and I want to know the effect of a line load, I will go to the chart of the line load. I have a line load with this value. I get all the parameters. I substitute here to get sigma Z due to the wall. Then I go to this point. This point is at a distance of R1 in this location. So I go to the curve of the line load. This is point load. This is the curve of the point load. I calculate it for this load. And instead of repeating myself, if this is 40 ton and this is 40 ton, and this is they are both at the same distance, then the effect of this point is the same as the effect of this point, or the effect of this load is the same as the effect of this load. Then I go to another point, which is this one. I take the distance, this inclined distance between them, I measure it. It is the same as the inclined distance here. With the same load, I get the effect of this point, load number 2, load number 3, load number 4, and then I add everything together. Then this is the cumulation of the all stresses. So this is what we are going to do. Each point, 1, 2, 3, 4, these are the 4 points, and this is the load. These are the results in a tabulated form, so that I can just calculate the effect of each one and get the summation. You have to check here. Yes, I multiplied by 2. This is what I was going to tell you to check. Because I just studied 1, 2, 3, 4. 1, 2, 3, 4. But I have another 1, 2, 3, 4 at this level. So I have to multiply the effect of 1, 2, 3, 4 by 2 again. So this 2 multiplied by the summation will give me the effect of all of the stresses at a 4 meter depth due to the effect of the wall and the point loads, which are the columns. This is how you do your how you use these charts, and from the influence line you cut the curve, and then you go down to get the value of the x, and so on. This in case of the line load. And then I sum both together, the effect of the line load with the effect of the concentrated load, to get all what I need. The next part of the lecture will be the uniform distributed load. We said that we studied the concentrated load, we studied the line load. Next step will be, suppose you have an area, you have a footing. I have a footing here, and I need to calculate the stress due to this footing, but at a distance of, say, 10 meters to the right and 5 meters below. How can I calculate this? This we'll discuss in the next part of the lecture. It will deal with many things. We have something called Newmark chart. We have many approaches because there are some constraints for using these methods. So how to apply it for different shapes of uniform load, it will take a little bit of time, so we'll have to start it in the next lecture, inshallah. So this ends up part 2 of our lecture, and we will continue next week, inshallah. Thank you.